Good afternoon, everyone. Welcome to our final session of Wednesday here at the SMPTE ATC. My name is David Long. I am from the Rochester Institute of Technology. Very excited to be leading today's session on perceptual color quality metrics for you. So in today's session, we have two papers. One will be on perceptual color difference metrics as they relate to high dynamic range displays. And we'll have another on observer metamerism indices as they relate to modern display light sources. Both studies will share a common goal of improving the quality of experience in exhibition through more perceptually accurate color metrology. And you'll also see examples of using improved color difference metrics for better display calibration and characterization. Our first talk is by Francois Helt. It is Metamerism, Color Ellipses and Color Errors. Francois has a background in mathematics, statistics, and filmmaking with 30 years of experience in professional video and film. He's been an R&D manager for teams dedicated to special effects software and worked with film scanners as well. He's been a technical manager of the European project Limelight, intended to build a complete digital film restoration system in the 90s. And more recently, he's been a technical director for Do-Re-Mi Technologies in Europe, chief scientific officer of Highlands Technology Solutions, and is currently a scientific consultant to Eclair Laboratories. Research interests for Francois include visual perception models, measurement theory, and philosophy of information, all of which you'll hear in this talk. So welcome, Francois.
Thank you, David. The title is misleading, in fact. It's not color errors, metamerism, and color ellipses are a way to measure how a proper coding could be used in cinema. So it's about cinema. It's about how you transfer the information, the color information from the conception to the distribution system. So yeah, there is two codes here which are totally different. One guy is saying that mathematics is part of physics. The others say the contrary. So anyway, there is mathematics everywhere when you're trying to model what's happening, and that's my favorite game, in fact. So this paper is about comparison between the index of Metamerism and color error standards, how it is measured. And it's not about the very recent color science. I mean, it's using very, very common and very old, in fact, ways of measuring color to see how you're doing the proper coding of color for a reproduction system. There has been a very recent study and proposition using PQ, so using measurements of the luminance and how it is perceived, how the modulation is perceived, and that's a Barton model, and it has been used to propose an equation, a function called the PQ for the reproduction system, but in fact, it's only a luminance system. So in reproduction, in fact, I'm showing this because it's quite interesting. The control of reproduction system, the control of coding from production to distribution to reproduction is based on the patches you see here. I mean, what is measured, what is controlled, and what the projector are trying to reproduce is in fact the color of the patches. The perception of the image is totally different. Even if the image is with the wrong colors or something slightly distorted, I mean, it will be perceived the same. This has to be keep that in mind. I mean, it's not perception and measurements of color is something different. So there has been a model that is being used and everybody is talking about, and you've heard about probably. It's the Barton model. Reading the book from Barton, it says explicitly this was used for luminance, and it's not about color at all. So it has been used to define the PQ transfer function called the ST2084 and used by SMPTE. Again, it's the reference. This is interesting, but it does not describe the relation between luminance and brightness perception. It's about sensitivity based on different, in function of luminance and frequency. So basically, the ordinary ways of transmitting color information is based on trichromacy, that is 3 dimension. Even if we discovered some more than 10 years ago that some people have 4 cones and not only 3. I mean, it's something that you may keep in mind, but it's the trichromacy is the way to transport ordinary images today. So a color usually can be described by RGB or XYZ, and it should be noted that XYZ is the basic thing for every computation on color. I mean, if you want to go from one system to the other, from one RGB to something different, whatever you are the color representation, you're going through XYZ. So a color is also luminance and chromaticity. Luminance has one dimension and chromaticity 2. And you can also define color by brightness, hue and chroma. What also must be noted is that every measurement, every expression of luminance and color is going through experiments, that a sum of experiment that is used to define what is luminance, what is color. For example, Barton has compared his model with 14 experiments, and he adjusted some parameters based on the analysis of those experiments. His model has been improved in the recent years by some other people, but still it's something that can be used to define the maximum sensitivity, even if it's changing from frequencies changing, but the maximum sensitivity can be used to define the modulation and how you code the modulation. So the luminance and color expressions are all based on the definition of a standard observer. And this standard observer, in fact, dates back from 1931. And it was defined using 7 observers, in fact. So it's really a very small group of people. And in 1931, I guess there was no Japanese, no woman, no young guy from elsewhere in the world. So it's the standard observer is something that is still in use to do measurements, to do estimation of color and luminance, but it's something that is really very specific and does not correspond to anybody's in particular, in fact. And all the color instruments are using this Standard Observer data to compute color and luminance, whatever the computation you can make after that. And I noted also that the instruments are based on, the instruments accuracy are 2%, but it's for the best instrument, but 2% is for one specific luminance, and not the one that is used in cinema. So it's the accuracy of this instrument is much higher, in fact. So in visual reproduction, you can divide the goals of visual reproduction in the accuracy of the visual reproduction in two different things. One goal is to measure the performance of the reproduction equipment, and I mean it's independent of any specific audience, any specific user of a theater. The other aspect can be related to the visual perception. And as I said, the Standard Observer is based on a very limited set of people. And the variability of perception is large. I mean, there are a lot of different ways, a lot of different characteristics, depending on the people. So one way of measuring the variation depending on the reproduction system is called the Metamerism, or, well, Metamerism is something that was developed because very different spectra can give the same color perception. And those color or those characteristic spectrum are metameric. That's the definition of metamerism. So, in fact, this is the basis for cinema and television. If metamerism was not existing, we could not have the same sequences, the same scene reproduced by different systems, and scenes that would look like the reality. So the spectrum of say, an orange or an apple in reality are different from the spectrum of the same orange or apple shown by a reproduction system. But you recognize the orange or the apple. So Metamerism is ensuring, in fact, this capability of having natural scene reproduction. So the spectrum of chromaticity, the point here I want to make is that the different equipment for reproduction are using different primaries, and they are using a different mix of those primaries to achieve the same perception of color. And this is here the rectangle is showing the color that is described by the small x, small y in the traditional chromaticity horse show figure. And you see here three different spectra, that are I computed that. I mean, it's approximation, but it gives a very good image of these differences. So one spectrum is the black body. So black body at a certain temperature is giving a certain color, and this color can be reproduced by a different system. There are something very close to the Xenon lamp. So I took Xenon lamp spectra and did the proper mix of primary to give the same color. And there is also a laser system. So laser have very narrow spectrum. So there are 3 lasers here that are showing, that are very close to the REC 2020, and are showing the same color. So in fact, it's nice to have this Metamerism system to be able to reproduce color correctly, but different spectrum will, for some people, give different perception of the color. So perception of this color is not very, very different, but it still exists. So there is changes if you change the luminance. We are here talking about real scene. The change of the observer, because the observer doesn't have the same perception of color, and the change of field size. So it depends on the structure of the eye. And there is a measure of the discrepancy, which is the index of Metamerism. So in one sense, Metamerism is the match of color, and index of Metamerism is the measurements of mismatch. It goes on the other way. So what we are interested in is a Metameric index for each Standard observer with, for example, a Xenon lamp system. The different people in the audience will have different perception because there is this variability, but the difference of perception will be limited because the Xenon spectrum has a certain shape. With a laser projector, the difference of perception of color will be higher. So to calculate, it's an old system, but to calculate the index of Metameric for the change of observer, the CIE, Commission Internationale de l'Éclairage, proposed a way of computing this based on a new set of observer, and it gave data called the Standard Deviate Observer. I mean, I always find that it's a bit fun to have a standard deviate. That's an oxymoron. Here on the graph, you show the standard observer data and the standard deviate observer data that is added to the standard observer data to give you a new set of color. As I said, you only have to add SDO data to SO data to have the index of Metamerism. So it's a deviation, but it's in fact this SDO gives you a new observer, which is not the standard observer, but a new observer. It's not giving you the full variations or how the variations can be described. It's something very specific. So unsatisfactory, but at least at the start. So as I said, the different projection system or projection system are having a different influence on the index of Metamerism for the change of observer. Here is a calculation I made many years ago showing the difference. So I'm using here calculation based on SDO and SO with a Xenon lamp system, a standard spectrum lasers with very narrow, about 1 to 2 nanometers width of each primary, each laser, and a wider laser. So we are trying to minimize the metamerism by having larger spectrum, larger peaks. So here it's 4 nanometers. So you see here that if you're using laser projection system, and putting the laser wavelength with the SDO data, you see that there are large deviations in the blue, and the blue laser is exactly at the maximum deviation. So basically what you will have is a change of color. But people are used to that. I mean, it's not that big. Another color measure that has been found and has been the basic work for trying to search uniform color space is called the macadam ellipses. Again, it's old, and it's based on one observer. So the set of observers is very limited. But it was showing that using XYZ with small x and small y, the color space is not uniform. Chromaticity is not uniform, and there are variations that are higher in some positions, especially towards the green. But that's a basic basic data to compute color differences. So color errors are there are a lot of new color errors that are used, and I'm talking about the ancient ones, CA Luv and CA Lab. It's not uniform, of course. If you want to have something which is going a long way to describe exactly what is the perception of colors, the new space is using various advanced mathematics, advanced function to compute the perception. But for myself, I found difficult to use system which is only describing 3 cones, as some people, not the majority, have 4 cones. How do you take that into account is a problem that I would like to understand better. Maybe next year. So all the formulas are using a very specific lightness, which is closer to the perception of luminance. So it's called L star. And we come to the calculation of GND, just noticeable difference. It was used to for the calculation of coding, in fact. So I'm coming to code just after this, just describing that there is specification in SMPTE documents that reproduction system must have a color error reproduction that is less or equal to 4 delta EAB. I don't know exactly the reason for this value. I think it was based on consensus and capabilities of the projector at the time it was defined. So you see 4 delta E and some of the Metameric index are around this, a bit higher. So when you code this as luminance is now coded, or there are propositions to code this luminance with PQ, that is with a perception quantizer, how do you code the color? The fact is, coding using numbers to represent values is adding errors, either integer or floating points. So you're using errors, or you're adding errors when you're coding things and transmitting back to the backhand. What is the amplitude of these errors? So that's one thing can be based on the Macadam ellipses. So even if the small x, small y color space is not uniform, I mean the minimum distortion, the minimum value can be found by using the minimum size of the ellipses and the circle inscribed in the ellipse. So the lowest semi-axis is approximately 0.3 by 10 to the power of 3. So if you're looking at the way things are transmitted today using x, y, x, so big X, with the transient function of 2.6, big Y prime, and big Z prime, you see that the maximum errors you're getting in color expressed in small x, small y color space is sometimes very high. And that if you were coding small x, small y information on linear, as small x, small y are going from 0 to 1 to cover the full color space, even if it's too much. I mean, using linear coding on 12 bits would give a value which is lower than the minimum given by the Macadam ellipses. So this is giving a possibility. I know changing the coding in cinema there are costs to that, and I'm not saying that everybody should change that, but there are costs and benefits. The benefits are, costs can be computed, benefits are more difficult to compute. But that would tend to demonstrate that a better coding would be big Y for luminance with the PQ function, and small x, small y in linear. So that's my point, in fact. Thank you.
Do you have any questions? We've got the microphone up here in the front for anyone.
Did you do any analysis of XYZ PQ and the color errors there relative to gamma 2.6?
Yeah, I understand. XYZ with 2.6 is better than using PQ for all three components, because PQ has a very derivative is very high, so distortion would be higher. I didn't do the exact computation, I must admit, but I didn't try.
All right, very good. Thank you, Francois.